One.
Hi, today we're going to be talking about how to calculate different frequencies of musical instruments. When you have musical instruments, they produce standing waves no matter what the instrument is. Now, when you have a standing wave, there are two parts to it. You have nodes, which are parts in the middle that do not move, and antinodes, which are the highest and lowest points. Now, these nodes and antinodes can vary with different frequencies of the sound. So you see when you adjust, you can get more or less antinodes. It all depends on the frequency of the instrument you're using. Now, there are three basic types of musical instruments. There's string, such as a guitar. There's open-closed, and open-open. For both of those, we can use a whistle for today's example. Now, for a stringed instrument such as a guitar, we have two different types of wavelengths. We have fundamental, which is 1/2 a wavelength, and we have first harmonic, which is a full wavelength. Now, for this, we measured that the length of the string on the guitar was 63 centimeters. So, since the length is 63 centimeters and we have 1/2 a wavelength being the fundamental, we would multiply this by 2 to get a wavelength of 1.26 meters. Okay, now we have this equation: velocity equals the square root of force tension divided by the linear density, the velocity being how fast the noise will travel in the conditions that you are, times square root of force tension, which is the tension that the strings are tuned at, divided by the linear density, which is the different density of the strings. Now you notice with a guitar, not all the strings make the same sound. Okay? And changing the tension will adjust the sound that the guitar puts out. Okay, so we have that, and just remember, if you have a full wavelength, your wavelength will be 63 centimeters, but if you have 1/2 a wavelength, you would multiply it by 2 to get the according wavelength, or however long your instrument string is. Okay, so now we move on to the next instrument, an open-closed instrument. With an open-closed instrument such as a whistle, you get antinodes on the top and bottom, and a node at the closed end. Now for this, we're going to use a length of 17 centimeters for the instrument. This picture shows that the wavelength is 1/4. That's the fundamental, and our first harmonic has a wavelength of 3/4. Now for this, we can use the formula velocity of sound equals 331.5 plus 0.6 times temperature Celsius to find our speed during the temperature in the room today, which is 21. So if we do 331.5 plus 0.6 times 21, we get 344.1. We get a velocity of 344. And again, that's the speed of the sound in the room today. Now we can move over to this equation. So now we use this formula: wavelength equals velocity over frequency, to find frequency, which is unknown to us at the time. So we have a wavelength of 17 times 4 centimeters comes out to 0.68 centimeters. And we have a velocity of 344.1 meters per second. After multiplying them out, we get a frequency of 506. 506? Yes. 506 hertz. Now that is our frequency for the 1/4 wavelength of the open-closed instrument. Okay, again, if you were going to be doing these, just remember that there's an antinode on the top and bottom and a node at the closed end. And again, the first harmonic is 3/4 wavelengths and the fundamental is a 1/4 wavelength. Okay, our second type of instrument is an open-open. For this, we can just open the end of the whistle and get a completely different sound. So for this, we see that there are antinodes on both ends and there is a node in the center. For this, we have a wavelength of 1/2 for our fundamental, and our first harmonic has a wavelength of 1. So we can use the same formula: velocity of sound equals 331.5 plus 0.6 temperature Celsius. Temperature hasn't changed, so the temperature is still 344.1. It's still the same whistle, so we have a length of 17 centimeters. Okay, so if we want to find our frequency for the fundamental, we'll use the same equation: wavelength equals velocity over frequency. We would multiply 17 by 2 this time because it's 1/2 a wavelength, so we have 0.34 meters. equals velocity, which is 344.1, over our frequency, which comes out to a frequency of
1012.
1012 hertz. Again, that's the frequency for the fundamental, and if you wanted just a shortcut, you could say that the frequency for the next one would be 2024 hertz.